July 10, 1942. A group of U.S. Navy mechanics stood on the windswept tundra of Akutan Island in the Aleutian chain, staring at what looked like the remains of a silver dragonfly. It was a Japanese fighter, mostly intact, nose buried in soft peat, wings twisted but still recognizable. The red circle of the rising sun had faded from weather, but the lines of the fuselage were unmistakable. The aircraft was a Mitsubishi A6M Type 0, the same plane that had outflown, outturned, and outfought nearly every Allied fighter during the first 6 months of the Pacific War. For the first time, America had captured one in flyable condition. The engineers didn't know it yet, but the machine resting in that Alaskan bog would rewrite how the United States designed, fought, and survived in the air. The discovery came almost by accident. A Navy PBY Catalina reconnaissance crew spotted something metallic while flying over Akutan, one of the uninhabited volcanic islands east of Dutch Harbor. They circled lower and saw the unmistakable outline of a Japanese Zero resting nose down in a marsh, its pilot still inside. The aircraft had crashed weeks earlier during an escort mission for bombers attacking the Aleutians. Its pilot, Petty Officer Tadayoshi Koga, had been flying low over the island when his engine took a hit from ground fire. Thinking he could make an emergency landing, he chose the open grass rather than the rocky coast. The ground, however, was not grass, but muskeg, waterlogged soil that swallowed the fighter whole. The impact flipped it gently onto its back, killing Koga instantly, but leaving the aircraft largely undamaged. In a war where most encounters ended in fire or deep ocean, that was a miracle. When the recovery crew finally reached it, they couldn't believe the condition. The propeller was bent, the landing gear destroyed, but the fuselage was intact. Even the radio equipment and instruments were salvageable. A recovery officer named Lieutenant Robert C. Larson quickly realized what they had found and ordered a full salvage operation. Within days, a team from Dutch Harbor returned with cranes, cables, and sleds. The aircraft was carefully winched free of the bog, its aluminum skin shedding mud like scales. They lashed it to the deck of a barge and sent it south to be rebuilt. The engineers on the receiving end would nickname it the Akutan Zero, after the place it had fallen. When it arrived at the North Island Naval Air Station near San Diego, the mechanics gathered around in near silence. Every man there had read combat reports describing the Zero's impossible agility, the way it could turn inside an American fighter, climb faster, and seem to vanish in a dogfight. Many thought those reports exaggerated. They weren't. When the engineers stripped away the panels and inspected the structure, their disbelief turned to something like awe. The aircraft weighed just over 5,300 pounds fully loaded, nearly 2,000 pounds lighter than a U.S. Navy F6F Wildcat. It achieved that through a combination of design choices that would have made any American safety inspector faint. The first thing they noticed was the skin. The outer shell was made from an aluminum alloy called Extra Super Duralumin, a Japanese innovation with high tensile strength but almost no corrosion resistance. The sheets were paper-thin, barely 1 millimeter in some areas. You could dent them with a thumb. Inside, the spars and ribs were drilled with hundreds of lightning holes, every unnecessary ounce cut away. Even the control cables were made of thinner gauge wire than U.S. standards allowed. It was engineering purity taken to its extreme. Nothing wasted, everything serving flight performance. But the cost was obvious. The Zero had no armor plating around the cockpit, no self-sealing fuel tanks, and almost no protection for the pilot. It could dance in the air, but a single bullet to its fuel line could turn it into a torch. The American engineers were both horrified and fascinated. Commander Eddie Sanders, one of the Navy's top test pilots, was assigned to oversee its restoration and flight testing. He later recalled that the Japanese designers had built the Zero like a bird, not a tank. When they finally rolled it onto the runway at San Diego for the first test flight on September 20th, 1942, the result stunned everyone watching. The aircraft lifted off gracefully at barely 90 miles per hour, climbed like a homesick angel, and could loop or roll with almost no control pressure. Sanders found that it could turn in a circle nearly one-third tighter than a Wildcat or P-40, and it held energy so efficiently that it seemed to float through maneuvers that would have stalled heavier planes. But as Sanders pushed it harder, its weaknesses emerged. At speeds above 300 knots, the control surfaces stiffened dramatically. The ailerons, responsible for rolling the plane, became nearly immovable. In a dive, it was fast but uncontrollable. At high speeds, an American pilot could dive away, regain control, and strike from above. It was the opposite of what the Zero's early mystique suggested. It was unbeatable only if you fought on its terms. As the tests continued, engineers mapped every performance metric they could. Maximum climb rate, 3,100 feet per minute. Range, an astonishing 1,600 miles on internal fuel alone. Maximum level speed, about 330 miles per hour. The range figures were what shocked the analysts most. The Zero could outfly almost every Allied fighter in endurance because of its massive fuel capacity, 156 gallons in unprotected tanks spread throughout the wings and fuselage. That endurance allowed it to reach far into the Pacific, escort bombers to distant islands, and still return. It explained how the Japanese had projected air power so far from their bases early in the war. The engineers drafted detailed reports for both the Navy and the Army Air Forces. Those reports circulated through every major design office in America. For the first time, they had data, not rumor. They could see the trade-offs, extraordinary range and agility bought by shedding every ounce of protection. To beat it, America would have to change how it built and how it fought. What followed was one of the fastest tactical revolutions in aviation history. Within weeks, test pilots were using the Akutan Zero to train fighter squadrons across the Pacific. They taught pilots what they called boom and zoom tactics. Never turn with a Zero, dive instead, attack from above, and use superior firepower and speed to stay out of its reach. Those tactics were later formalized in combat manuals distributed to every Navy air group. When combined with the arrival of new fighters like the F6F Hellcat and the F4U Corsair, both designed with lessons from the captured Zero, the balance in the Pacific began to shift. But back in 1942, that future was still uncertain. As the engineers and pilots stood around the Akutan Zero on that first flight day, they realized they were looking not just at an enemy machine, but at a mirror of their own limitations. American aircraft were strong but heavy, safe but sluggish. The Zero showed what happened when you pursued performance with no margin for safety. It was genius in its own right, beautiful, deadly, and doomed by its perfectionism. The Akutan Zero would fly dozens more test hours before a mechanical failure in its landing gear finally grounded it for good. By then, its secrets were long extracted. Its lightweight frame had taught America how to build faster planes. Its vulnerabilities had taught pilots how to survive. In the end, it was a gift from an enemy that had never meant to give one. The Akutan Zero sat in a hangar at North Island surrounded by clipboards, calipers, and flash cameras. Its skin gleamed under fluorescent light, silver and thin as foil. Engineers from the Navy's Bureau of Aeronautics and Grumman Aircraft Corporation came and went in shifts, measuring every rivet, photographing every component. The captured fighter became a classroom. They studied how its control cables ran in perfect, frictionless arcs. How the canopy rails were machined to such precision that they could slide under their own weight. and how the designers had trimmed the engine mount down to the minimum thickness that could still support stress loads at high G-forces. To American eyes accustomed to overbuilding for durability, it seemed reckless. But to Japanese engineers, every ounce of structure was an ounce of lost range. What made the Zero's performance possible was not one trick, but a philosophy. Jiro Horikoshi, its chief designer at Mitsubishi, had been obsessed with lightness since his university days. He believed that a plane which never got hit didn't need armor. His A6M embodied that belief completely. The fuselage was designed like a glider's, smooth, aerodynamic, and free of drag-inducing interruptions. Its wings had a continuous spar running from tip to tip, which gave the Zero remarkable strength for its weight, but also made repair difficult. American fighters used detachable panels and modular components. The Zero was seamless, organic, almost alive. The U.S. test pilots who flew it said it felt like an extension of their own reflexes. Commander Eddie Sanders reported that it answered the controls as though it read your thoughts. But he also noted the unsettling fragility. During one high-speed dive test, a rivet popped loose from the wing root, and the vibration nearly tore the panel free. When he landed, he said to the ground crew, "This thing flies on faith." As reports circulated through Washington, American aircraft designers began applying what they'd learned to ongoing programs. The F6F Hellcat, still in prototype testing, was given a new Pratt & Whitney engine and revised wing geometry based on insights from the Zero's lift characteristics. Grumman's engineers realized that they didn't need to match its lightness to beat it. They only needed to counter its style of fighting. The Hellcat would be faster in a dive, stronger under G-load, and capable of absorbing punishment the Zero couldn't survive. Meanwhile, intelligence officers at the Naval Air Station documented everything for tactical distribution. Their preliminary analysis of Japanese fighter Model 00 became required reading for every pilot deploying to the Pacific. It described in plain language what the Zero could and couldn't do. At low speed, it could outturn anything in the sky. Above 300 knots, it became stiff and unresponsive. It could climb fast, but couldn't dive as deep without risking structural failure. Its engine, a Nakajima Sake 12, lacked a supercharger, giving it excellent mid-altitude performance but poor power above 20,000 feet. Those pages, written in measured technical language, would save thousands of lives. At first, some pilots didn't believe the reports. The myth of the invincible Zero had taken root early in the war, an enemy ghost that seemed to defy physics. But training with the Akutan Zero made the myth vanish. At the Navy's air station in San Diego, pilots began mock combat flights against the captured plane. Instructors demonstrated that by diving, then climbing into a high-speed pass, they could attack from above and roll away before the Zero could follow. "Never dogfight," they told the rookies. "Use your speed, not your stick." These lessons reached the front lines just in time. By late 1942, the Guadalcanal campaign was raging. American pilots flying Wildcats and P-39s were still outmatched in one-on-one turning fights, but they were starting to use energy tactics. Hit-and-run maneuvers perfected in the skies over California using the Akutan data. The results showed quickly. The kill ratio, once as bad as 3-to-1 in Japan's favor, began to narrow. Back in the hangar, engineers dismantled the Zero's engine and found more surprises. The Sake power plant was simple, compact, and immaculately balanced. It used an unusually high compression ratio, giving good performance on limited octane fuel. The carburetor system, though primitive, provided a steady mixture at steep climb angles. One reason Japanese pilots could pull vertical loops without stalling out. Yet, it lacked armor and self-sealing fuel lines. American analysts drew a direct conclusion. The Japanese had traded survivability for range and maneuverability because they expected their pilots to win through skill, not endurance. To verify the theory, the Bureau of Aeronautics rebuilt the power plant at Wright Field in Ohio. There, Army engineers ran it side by side with an Allison V-1710 from a P-40 Warhawk. The Japanese engine produced 940 horsepower at takeoff, nearly identical output, but weighed 300 pounds less. Every component had been pared to its limit. The propeller spinner was hollow aluminum, the exhaust pipes paper-thin. It was an engineer's version of a samurai sword, sharp, elegant, and fragile. The intelligence summary that emerged from the Akutan project went to every Allied partner, including Britain and Australia. For the first time, they understood the pattern behind Japan's aircraft. Agility over armor, range over redundancy. The report noted that Japanese aircraft construction is characterized by exceptional craftsmanship, but at the expense of protection and service life. It is a weapon of immediate advantage, not sustained campaign. That insight shifted Allied thinking. The Pacific War would not be won through duels, but through attrition. America would build aircraft that could take hits, return home, and fight again tomorrow. The Akutan Zero continued to fly through early 1943 under careful supervision. Each test flight yielded new data: stall behavior, roll rate, climb curve, turning radius, fuel consumption. Engineers even tested aerodynamic buffeting at varying flap angles, plotting graphs that later guided U.S. Navy fighter design for years. But as the Zero's value as a test aircraft faded, its symbolic power grew. To every mechanic and pilot who saw it, it was proof that knowledge could change a war more than firepower could. When the Zero was finally retired from flight testing, after a landing accident in 1943, the wreckage was preserved for study. Its frame was measured down to the rivet spacing. Every inch had been catalogued. It had served its last mission not for Japan, but for the country that defeated it. By mid-1943, new American fighters were rolling off assembly lines, heavier, faster, and designed with one guiding principle: never fight the Zero's fight. The Akutan discovery had turned a weapon of terror into a teacher. By the summer of 1943, the Akutan Zero's influence had spread far beyond the hangars where its pieces were studied. At every naval air station from Hawaii to Guadalcanal, instructors repeated the same phrase to new fighter pilots: "Don't turn with a Zero." Those 4 words, born from test data and confirmed in mock battles, became the unofficial creed of American airmen in the Pacific. For pilots like Lieutenant Butch O'Hare and Commander John Thack, the Akutan findings didn't just confirm what they'd suspected. They gave them hard numbers to build new tactics. Thack, already famous for his weave maneuver, began incorporating the captured Zero's climb and roll rates into training exercises. He knew that the Zero could outturn any Allied plane below 200 knots, but at higher speeds, its ailerons stiffened so badly it might as well have no wings. So, he taught his men to dive, shoot, and climb away, a rhythm that would later become the hallmark of American aerial strategy. By late 1943, the data from the Akutan Zero had filtered into the design offices at Grumman, Vought, and Lockheed. The engineers there weren't trying to copy the Zero, they were trying to beat it. At Grumman's plant in Bethpage, New York, test pilots flew prototypes of the new F6F Hellcat. It was heavier, thicker-skinned, and far less graceful than the Zero. But when they compared performance sheets, they saw the payoff. The Hellcat could dive faster, take more damage, and keep its control authority well past 350 knots. In combat, that meant choice. The American pilot could decide when to fight and when to leave. Meanwhile, at Vought Aircraft in Connecticut, the same lessons shaped the F4U Corsair. Its inverted gull wings and massive engine made it the opposite of the Zero in every way. a brute built to fight on its own terms. Engineers even tested Zero-style control surface balancing and rejected it as too light for combat wear. The Americans had learned that sometimes the best weapon wasn't perfection, but forgiveness. The Zero gave no room for error. The Hellcat could take a hit, stall out, and still fly home. When the first reports of combat between Hellcats and Zeros came back from the Pacific in late 1943, the numbers stunned the Navy. During the Battle of the Philippine Sea, what pilots later called the Great Marianas Turkey Shoot, Hellcat pilots achieved kill ratios as high as 13-1-1. The same aircraft that had terrorized the Pacific skies in 1941 were now burning in dozens. What had changed wasn't just hardware, it was knowledge. The engineers who had studied the Akutan Zero had passed their understanding to the pilots, and the pilots had turned that knowledge into survival. But the respect never faded. Test pilot Eddie Sanders, who had logged more hours in the Akutan Zero than anyone else, wrote in his post-war notes that it was the finest light fighter ever built within its design intent. He meant that sincerely. The Zero wasn't a failure. It was a masterpiece built for a very specific war, a short, aggressive campaign Japan hoped to win before American industry could respond. When that plan failed, the same design strengths became liabilities. The long-range fuel tanks that had carried it across the Pacific also made it burn fiercely when hit. The paper-thin skin that gave it unmatched agility couldn't stop a single .50 caliber round. At Wright Field in Ohio, engineers used the Akutan Zero's data to refine airframe fatigue models and fuel system designs. They found that the lack of self-sealing fuel tanks was responsible for nearly 80% of Japanese aircraft losses to fire. Within months, American planes began incorporating multi-layer rubberized bladders and inert gas systems that reduced explosions by half. Even lessons from what not to do had practical value. By early 1944, the captured Zero had become more than a test subject. It was a benchmark. American engineers compared every new prototype against its flight data. The North American P-51 Mustang, though a different class entirely, was tested for climb and roll rates using the same figures derived from Akutan. In official documents, the Zero's data table was still labeled Enemy Fighter Number. While American pilots used the knowledge to win battles, the Japanese pilots who once flew the Zero were trapped by the same design they had once worshipped. As the war dragged on, Japan lacked the aluminum alloys and precision manufacturing needed to produce replacements of equal quality. Later Zeros were heavier, slower, and often poorly riveted. The aircraft that had started the war as a symbol of supremacy ended it as a desperate weapon flown by undertrained recruits. When the war finally ended, the Akutan Zero was moved to storage at the Naval Aircraft Factory in Philadelphia. Its once polished fuselage dulled with oxidation, and its wings, once the envy of every engineer in the Pacific, gathered dust. In 1945, a hangar accident damaged the airframe beyond repair, and the remains were quietly scrapped. Only its engine and some control panels were preserved. For a time, it disappeared from memory. But its legacy lived on, in the manuals, the data sheets, and in the way American fighters were built for the next generation. In the 1950s, historians rediscovered the story and interviewed the men who had worked on it. Every one of them said the same thing. The Zero had been their greatest teacher. It had shown them that even an enemy's perfection carried flaws, and that victory came not from imitation, but from understanding. The aircraft that once symbolized Japan's dominance in the air had, in its broken state, handed the United States the keys to winning it back. For the American engineers who first found it half buried in that Alaskan bog, that realization came years later. They hadn't just salvaged a wreck, they had salvaged the future. After the war ended, The Akutan Zero's influence lingered in the minds of the engineers who had studied it. The aircraft itself was gone, its remains scrapped in a forgotten hangar, but its legacy had taken root in American engineering philosophy. For decades after 1945, its fingerprints would appear everywhere, from jet fighters to the way designers thought about weight, lift, and performance balance. At the Naval Air Test Center in Patuxent River, Maryland, a young generation of engineers trained on wartime case studies, including the Akutan Zero analysis. They learned a lesson that would echo through the jet age. Perfection in one dimension is failure in another. The Zero's unmatched agility came from obsessive weight reduction, but that same pursuit of lightness destroyed its ability to absorb punishment. The first jets, like the F-86 Sabre, embodied the opposite approach. They were heavier, more stable, and built to survive combat damage rather than evade it entirely. Designers at North American Aviation specifically cited wartime lessons about energy fighting, maintaining speed rather than relying on low-speed turning. That doctrine, born from studying the Zero, became the foundation of modern aerial tactics. The Zero also influenced American materials science. The Japanese alloy used in its skin, extra super duralumin, was analyzed and replicated in U.S. laboratories. It was strong, yes, but hopelessly prone to corrosion. The engineers at Alcoa took that finding and created new alloys like 7075 T6, which combined the same strength with far better resistance to fatigue. The first American aircraft to use it extensively was the P-51H Mustang, followed by the B-47 Stratojet and the F-86 Sabre. In every case, the designers referenced the Zero's weight efficiency as something to emulate, but safely. At Wright Field, aerodynamicists studying the Zero's performance data noticed something else. Its clean airframe and smooth wing surfaces produced exceptionally low drag for a propeller-driven aircraft. In the jet era, those same principles applied directly to transonic flight. When test pilot Chuck Yeager broke the sound barrier in 1947, the engineers who designed his Bell X-1 had pored over the Zero's data tables, among others, to understand how to reduce form drag and maintain control through high-speed compressibility. It was a strange lineage, the lessons of a 1940s Japanese fighter shaping the first supersonic flight. But history often works that way. In Japan, the end of the war silenced aircraft production, but not the minds behind it. Jiro Horikoshi, the Zero's chief designer, survived the war and later became a professor at Tokyo University. In his post-war memoir, he admitted that he had known the aircraft's weaknesses from the beginning, but was bound by Japan's military doctrine. They wanted a plane that could not lose. I told them it would win every duel, but not the war. His humility resonated with engineers around the world. The Zero, once a symbol of imperial ambition, became a case study in the limits of idealism. American aviation schools taught the same lesson differently. At Caltech and MIT, post-war aeronautical engineering courses included sections on lightweight combat design. Professors cited the Akutan Zero as a warning: never let performance compromise survivability. Students trained on that philosophy would go on to design the F-4 Phantom, the F-15 Eagle, and the A-10 Thunderbolt, all aircraft built on the principle that strength and range mattered as much as speed. The Zero also shaped human perception of air combat. Before its discovery, most American designers thought of airplanes as machines of brute force, armor, horsepower, and firepower. The Zero proved that elegance could be equally dangerous. It reminded everyone that engineering was as much art as science. That idea survived into the space age. The engineers who built Apollo's lunar module later referenced the Zero's weight philosophy. Cut everything that doesn't make it fly. The result, a craft that looked fragile but worked perfectly, owed a quiet debt to an enemy plane pulled from an Alaskan swamp decades earlier. By the 1960s, few of the men who had first seen the Akutan Zero were still in service, but their reports continued to circulate in technical archives. The data they collected became historical, but the moral stayed alive. In every engineering field, from aerospace to automotive, the same balance appeared again and again: lightness versus strength, performance versus safety. The Zero was the first aircraft to make that trade-off so starkly visible. In 1974, a restored Zero built from surviving parts appeared at the National Air and Space Museum. Among the visitors that day was Eddie Sanders, the Navy test pilot who had flown the Akutan plane in 1942. Standing beside the exhibit, he told a reporter, "It's easy to think we beat it, but really, we learned from it." Then he added almost quietly, "We won because we listened to what it taught us." For historians, that was the real ending of the Akutan story. Not the crash, not the tests, not even the victories that followed, but the transformation of understanding. The Zero, designed to dominate the Pacific through grace and speed, had instead become America's most valuable teacher. Its thin skin and light frame spoke louder than propaganda ever could. That brilliance without balance is brittle, and that in engineering, as in war, survival favors those who learn faster than they build. And so, on that cold island in the Aleutians, when the salvage crew first saw its fragile wings glinting in the mist, they hadn't just found an airplane. They had found a mirror, one that reflected not just an enemy's genius, but the path forward for those who would one day surpass it. Thanks for listening till the end. I put a lot of effort to bring you factually correct and lesser-known stories of the past. Subscribe my channel if you like this type of content.